This lecture is the nature of the four fundamental theorems of calculus in three colors: black, green, and red. So let's begin with single variable calculus. And here I've already written out the equation. What it says is, in black, if we start with the derivative of the function, f prime of x, and then in green we move to integrate that function from a to b, the fundamental theorem says that the answer is equal to, in red, the value of the function at b minus the value of the function at a. So the answer is associated with the boundary. What this says is, for example, the area under the rate of change curve, 42 in this example, is exactly equal to the length of this line segment. In multivariable calculus, we have three theorems. The first is line integrals, often known as the gradient theorem. And here we have a line in space, really a curve in space, and it's bounded by points P and Q. And here we're going to measure with a line integral work. We also have a vector field F shown here. Now the idea behind this theorem is, if we can find a scalar function little f called a potential function such that the gradient of f equals that vector field f, then we can write first in black, we can write the derivative function, which is the gradient of little f, the potential function. So we start with that in black. We now change color to green, and we integrate over that function from P to Q, or in general we're integrating over the curve. Now we need to complete the symbol of integration, so we have to dot it, as the gradient of f is a vector, and we're going to dot it with dr, the element of integration. So at a point, say here, we have a dr, a change in the position vector. Okay, so we have the integral of the derivative. The third and final step is to change to red and evaluate the integral of the derivative. So here we write equals to in red, and the answer is to look at the boundary. So in this case, for line integrals, the answer is going to be the potential function f evaluated at q minus the potential function f evaluated at point P. So there we have it. The integral of the derivative is, as a physicist or a chemist might say, the change in potential. We now move to Stokes Theorem, which is necessarily defined in space, R3. This is Stokes Theorem. And here we have a surface shown in green, and this surface is bounded by this curve here. We also have our vector field f, and we're going to be measuring this time flux through the surface, flux or flow. So we begin by taking some kind of derivative. Now that derivative is called the curl of f, and it too is a vector field. We define it as del cross f, and the formula is rather complicated, so we won't show it here. But what curl of f is a measure of how at the surface things are rotating. So here's an example of a vector associated with the curl of f. this vector points in the direction that is perpendicular to the plane of maximum rotation. So let's begin with the curl of F, and we write it as del cross F, the vector field F. The second step is to change color. We're now going to integrate over this surface, so that's going to be a double integral, a surface integral. And because we're working with a vector field here, F, this double integral is often called a flux integral. Now this is a vector here, so we need to dot it with the element of integration, and that's simply going to be ds. So now we have the integral of the derivative. The fundamental theorem says, let's change to red for our answer at the boundary. So where's the boundary of this surface? Well, the boundary is here. So this is a little bit hard to draw, but you get the idea. Now what is this? This is a curve, and it has orientation. So let's say we're going in this direction for our dr, and this curve is closed. So our answer, according to the fundamental theorem, is to evaluate that boundary, and that's simply a line integral, which happens to be closed, so it's defined over the curve, and the value to integrate is f, the vector field, dot dr. So we have the integral of the derivative is equal to the line integral f dot dr. The answer is in the boundary, and that's the point. Okay, in the last case, we have the divergence theorem, and now we're working with a solid, W for solid. So we again have our vector field F. So we need some kind of derivative to begin. The derivative in this case is going to be divergence, and we define divergence as del dot F. So it's a scalar. It's not a vector, and it's the sum of the partial derivatives of the components of the vector field F. So again, we start in black with the derivative, del dot F. Okay, here's our derivative. We change color to green. We're now going to integrate over this solid. So this is not a vector, this is a scalar, and we're necessarily in R3 here. So when we integrate, we'll be taking the triple integral over that solid. This is a scalar, so there's no dot here, and the element of integration is going to be dv, which is equal to dx dy dz. So we have the integral of the derivative as before. The answer is, in red, equal to, well, let's look at what's going on at the boundary of this solid. Well, the boundary is just the surface of that solid. So what's going on here is flux. We have this vector field and a surface, so the value at the boundary that we care about is a surface integral over S of F dot, and the element of integration as before is ds. So what we're saying is, a physicist would look at this and say, the flux, or the flow through the surface, is exactly equal to what's going on inside of that solid in terms of divergence. And divergence, I don't think I mentioned this, but divergence is a measure of how things are stretching or compressing. In fluid dynamics, we call that a source and a sink. So here's your fundamental theorem for solids called divergence theorem due to Gauss. And a mathematician would look at this and say the integral of the derivative is the value at the boundary.